Welcome back, ladies and gentlemen. Thank you so much for attending the 2021 U8 World Innovative Summit Spring Conference from all around the world. I'm the host today, Peng Zhuyu from MIT. Today, it's a great pleasure to have invited Professor Neil Gershenfeld as our valued guest speaker. Professor Neil Gershenfeld is the director of MIT Center for Bits and Atoms, where his unique laboratory is breaking down the boundaries between digital and physical worlds, from pioneering quantum computing to digital fabrication to the Internet of Things. He's a CNN Time Fortune Principal Voice and has been selected one of the top 100 public intellectuals. He's also a fellow of American Association for the Advancement of Science and also American Physical Society. He has also been named as one of the Scientific American's 50 leaders in science and technology. During the speech, if you have any questions, please feel free to type them in the Q&A box below, and we're going to have a Q&A session at the end of the speech. Now, without further ado, please join me to welcome Professor Neil Gershenfeld for his talk.
Hi, happy to join you. Is my audio, video, and screen good?
Looks great.
Okay. So I direct the Center for Bits and Atoms at MIT. For background, we were created to study the boundary between physical science and computer science. I never really understood that distinction. So we've done things like the first quantum computations that were faster than classical, doing Shor's algorithm for factoring, Grover's algorithm for searching. We developed how to do cryptography in materials with mesoscopic light scattering, how to do universal logic in fluids with microfluidic bubble logic. We were part of creating minimal synthetic organisms, part of the birth of Internet of Things, part of using digital circuits using analog device degrees of freedom. All of these questions where you just can't separate hardware from software. So that's the kind of research CBA was created to do. Then the people who do it range from Justin, who built and still runs all the computers at Facebook, and Rafi, who built all of Twitter's computers. And I don't really think of myself as a computer scientist, but to do that, you can't believe in computer science effectively. You have to take millions and millions of dollars and megawatts of power and tons of mass and turn it into information. And so you need to think much more deeply about how the digital and physical worlds relate. So these are some of the people and some of the companies that have come out of studying this boundary between digital and physical worlds. Mac started Formlabs, now a $2 billion unicorn. Amanda recently figured out how to unlock lock letters, projects like those. And what's coming out of that work is the connection between computation and fabrication. So this is the most important graph in history. During these years, Gordon Moore plotted these 5 points. He went on, of course, to found Intel. And he showed that, noticed that on a logarithmic plot, they lined up, suggesting they were doubling. And in a very influential paper, he projected, what if that went for 10 years? This came to be known as Moore's Law, that defined the digital revolution. He never called it Moore's Law. But he had this prescient article projecting the digital revolution, and he only got one thing wrong, which was instead of 10 years, it was 50 years. So this graph shows the mainline Intel processors. This was 50 years of Moore's Law scaling that have come to define the last few decades. What I'm plotting here is now one measure I'll describe of not digital communication or computation, but digital fabrication. And you see that lines up like an exponential. This has come to be called Lass's Law after Sherry Lassiter, somebody who works with me at MIT. And there's more data here than Gordon Moore had when he first forecast Moore's Law. And so it's only rational to ask, what if this trend continues for the next 50 years? What does 50 years of a digital fabrication revolution look like? Not replacing, but completing the digital revolutions in communication and in computation. So to start, what I want to do is try to look at 50 years of scaling to come. So let's start with, there's one Earth, and in 1952, MIT invented computer-controlled machining. So this was the first time a real-time computer was connected to a machine to make parts. And that grew out of the Project Whirlwind. Initially for radar systems, MIT developed the first large-scale real-time computer that filled 2 floors of a building just off of campus. And around that time, jet aircraft were emerging. And the parts were too difficult to make by hand by turning cranks on a machine. And so these very dissimilar worlds got connected with the idea of a computer controlling a machine. So that was the birth of computerized manufacturing. And the lab I run today, you can think of as the descendants of that. We have one of every kind of tool, from nanostructures to microstructures to mesostructures to macrostructures, to both excuse me, measure objects and make objects. And to a great extent, these still all work the same way as that 1950 tool. A computer moves motors with an end effector that either deposits or removes material. So these are the modern descendants. So in turn, there's a few thousand cities on Earth. And what came after the whirlwind was the mini computer era. And what's coming after the MIT NC Mill is now the Fab Lab era. So from the whirlwind computer, MIT's Lincoln Labs transistorized it. The transistorized computer was commercialized by Digital Equipment as the PDP. And in this picture at Bell Labs, Ken Thompson and Dennis Ritchie are in the process of inventing Unix. And this is the moment when word processing, the internet, video games, all of the things pretty much you do on a computer today happened in this era. It cost $100,000 and filled a room, which was too much for one person, but was on the scale of a work group. You didn't need a whole corporation. And it led to this birth of the flowering of how modern computers work today. So to a surprising extent, if you're looking at a computer now, or if you have a computer in your pocket, how it works, it really emerged right from that historical moment. So I appreciated that analogy when once I set up a lab with all of those machines, it would take a lifetime of traditional classes to learn to use them. So with colleagues, I started a class called How to Make Almost Anything, aimed at just a few research students to learn to use those tools. And I wasn't prepared for every year, hundreds of students try to get in the class. And in fact, it's grown to multiple labs at MIT and even a Harvard lab for the MIT class. And every year the students do the most remarkable things. The first year I taught it, Kelly made a device to save up a scream when you're mad and play it back later. And this was a web browser for parrots. And this was an alarm clock you wrestle with to prove you're awake. And this is a dress that defends your personal space. These really fun projects, but they helped me appreciate what they were really showing was just as the killer app for digital computing was personal computing. And outside of Boston was the whole mini computer era industry that failed when computing became personal. The students were showing that the killer app for digital fabrication is personal fabrication, not mass manufacturing, but manufacturing for a market of one person themselves. So that then led to the Fab Lab project for the National Science Foundation, which funded this creation of Center for Bits and Atoms. To do outreach rather than telling people what we were working on, we thought we would let them do it. So in between the tools on campus and where the research is headed that I'll describe, we took a snapshot in between. So this is about 2 tons of material, about $100,000, fills a big room. It's about the cost and complexity of a mini computer. It includes a 3D printer, but it includes tools for precision machining that can make dense circuit boards, surface mount rework, large format machining, molding and casting, laying up composites, range of tools to create complete functional systems. And so with those tools, you can make boats, bicycles, furniture. This is a whole solar house. This is a citywide internet, communication infrastructure, healthcare instrumentation, consumer products, production tooling. These were done not in a factory, not by a business, but just by using the tools in these labs. And we had an unexpected accident. We opened one in inner city Boston for outreach. A connection led to doing one in Sekondi Takoradi in Ghana. That led to doing one in Pretoria in South Africa, which grew to one above the Arctic Circle in Lyngseidet, Norway. And ever since, they've been spreading all over Earth. So about as far north as you can go in Europe, as far south in Africa, rural, urban locations. We didn't plan that spread, but all over the world, every time one of these labs opens, it spawned the creation of another one. And the graph I had showed you before shows the doubling, how the spread of access to these tools has been growing exponentially. And so to give you a feeling, this is one in Detroit working with at-risk youth. This is one in Bhutan, where the economy is not based on money, but gross national happiness, measures of well-being, but they would buy products made far away to make it locally, at a boundary in Israel, at a boundary in Northern Ireland, arts colony in Maine with Alaska natives. All of these places getting access to state-of-the-art advanced digital manufacturing. We couldn't think of pushing it to those places, but each of them pulling it to bring it. So to keep up with that, I started a program called the Fab Academy to teach these skills globally. And that spawned a number of other classes, including with my colleague George Church at Harvard, a bioacademy. And the way this works is very different from a traditional class. In a traditional class, you come to a central location. In an online class, you look at a screen. This is distributed. So instead of 100 students, there's 100 labs. Each lab has a group of students locally with mentors, peers, machines, and then we connect those globally. And this is an example of homework in that class. So this was in a lab outside Barcelona. Guillaume was interested in food. In the beginning, all he could do is make a picture. And then he's starting to learn CAD. And then he's learning rapid prototyping to make a small model. Then he's learning large format machining to make a big model. Then he's learning instrumentation. Around here, he's learning to design electronics and interface sensors and actuators and write embedded code to make the intelligence. And so this is developing an aquaponic system. Here's the controls for it. And then he's starting to boot up the system. And I love this picture then. Around here, he has the first lettuce from the system. And again, it's not a startup, a team, a business. Just once you master these means of expression, all of this was the homework of a beginner in a rapid prototyping class. So you can think about MIT sort of like a mainframe. It's very effective, but you go there for processing. You can think about online classes like time sharing. They're still a central site. The way the Fab Academy is working and these other classes in what's come to be called Academy is it's more like the internet. It's a network of educational nodes. So as I mentioned, there's a follow-on class in biotechnology, how to grow almost one. There's a Fab Academy on textile technology. There's classes coming on things like Agri-Academy on agricultural technologies, all using this distributed educational model. So as these labs spread, just as outreach initially, there were a number of surprising implications. So this is Barcelona's mayor. Barcelona has a fabulous design sense, but over 50% youth unemployment. The economy is really broken for a generation. And so he's starting a 40-year countdown to urban self-sufficiency. The idea is instead of bringing in products and sending out trash, having the means to produce what they consume within the city. These are all cities who have joined that initiative. This is a lab we ran at the White House in the Obama administration. That's led to the introduction of this bill that's just about to get reintroduced in the US Congress.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress. But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or for part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives, which supports the goals and mission of the National Fab Lab Network as in the best interest of our people and the best interest of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have the chance to visit Neil and see the...
So the US has national labs that are billion-dollar facilities with guards that are inaccessible to ordinary people who has a job to impact the life of the country. This is chartering a national network of local labs with a goal of universal access to digital fabrication as a new kind of right in the same way we expect access to communication or computation. So that's just getting reintroduced in the US House and Senate. And so what this leads to is some of the most sensitive issues today include things like diverging incomes, tariffs, battles over infrastructure. And those all assume consumers have jobs to get money to purchase things, then factories produce them, then supply chains ship them. And this isn't utopia, it's not free, but if you have widespread access to the means to turn digital data into physical things and physical things into digital data, it means you can do much more sustainable production locally, replacing a lot of the assumptions that go into an economy today. And so the really very fundamental questions about how economies functions and how societies are organized are challenged by the spread of this access to these tools for digital fabrication. In a way, it's very old, going back to the notion of local sustainability, but it's also very new because to do this, it rests on global connectivity for data, for knowledge, but then the means to produce locally. And we talk about those in these articles. To see the implications of that, this has been really driven by the pandemic. So when the pandemic hit, in the immediate response, while the heroic work was done, like you heard just before, in developing the vaccines, there were a number of urgent needs for personal protective equipment, for respiratory assistance, for medical testing. And there was a big gap. On one side was traditional manufacturing that can scale, but takes a long time to ramp up. On the other side, there were do-it-yourself projects that can prototype, but can't scale. And what came out from that is a research initiative that I helped coordinate at MIT that curated best practices. So things like doing computational fluid dynamics to study virus particle propagation and doing nanoscale imaging of the performance of filter media and structural modeling of kirigami structures. And coming all out of that were designs for things you can produce through the life cycle of PPE testing, respiratory assistance recovery, that could then get propagated through the network, sent digitally, globally, and produced locally. And this scaled up to produce items, quantities in units of millions, not in a central factory that then had to be shipped, but again, by shipping data and producing locally. And so this vision of think globally, fabricate locally, that the research was heading towards, was really demonstrated and accelerated by the urgency of responding to the pandemic. And these are some programs that talk about it. This was a MAKE program. And then this was once a year, this global network gathers. It was online during the middle of the pandemic. This is a program describing how the distributed network rallied to produce this. And in this case, it wasn't just a nice thing, an optional thing. It was really an existential, an urgent thing. And most recently, this has spun up again during the crisis in India. A team there is developing oxygen concentrators around an open design that can then be produced in a distributed way. And once again, the oxygen concentrators raise some very substantial research questions that a global team is helping them develop. So once a year, as I mentioned, all this global network gathers. MIT hosted it a few years ago. A year after that, the whole global network came to Shenzhen, the beloved home of a lot of the technology behind the network. And the next gathering is coming up this summer. It's hosted in Montreal, but there's regional gatherings all around the world. And so if you're interested in learning more about this, this is a good next step to connect with the network. So then I want to look at continuing scaling. So from thousands of cities on Earth, there's millions of towns. And what came after the mini computer era was the hobbyist computer era. The Altair wasn't really useful, but it was personal. And the homebrew computer club that became Apple started on an Altair. Micro-Soft that became Microsoft started on an Altair. And the analogy with that is now machines making machines. So in the research we've been doing on digital fabrication, we've had to revisit the internals of CAD, CAM, machine control, motion control. And that's led to many companies that make machines like Formlabs or Fablite or Bantam Tools or Shaper. All of these spun off from the work on campus, and they made advanced manufacturing faster, better, cheaper, much more accessible. And Formlabs recently reached a $2 billion valuation. So in one sense, that's a success, but in another sense, it's a disappointment because you still need the global supply chain to buy the machine to make the things. So the real goal isn't rapid prototyping, it's rapid prototyping of rapid prototyping, using the machines to make the machines. And this is the kind of architecture emerging from that. This is work of my student, Jake, where you start with parametric axis generators, you compose them into a machine that does an operation. And then the controls he's showing here are actually a distributed computer. It's not simply a motor controller, it's a distributed data flow network in hardware. And then in software, you develop a control algorithm and you overlay the software controls on the hardware controls. And so a machine might have 3 or 4 or 5 axes. It might be open or closed loop. But traditionally, those steps of CAD, CAM, machine control, motion control are done by different people at different time, erecting barriers. Here, they're all overlaid. They're all digital and virtual. And so you can change them quickly to do rapid machine building. And once again, the pandemic really accelerated that. The classes we ran that required access to tools in the lab, we couldn't run when people are at a distance. And so instead, what we did is we took the machines in the lab, we used them to make generations of machines. We then sent the machines to the students where they were able to do the hands-on work in the class. And so rather than bringing the students to the lab, we brought the lab to the student, which is something we knew was coming in the future, but the demand of the pandemic, again, accelerated the need for that and brought it home much more quickly. And so this is a rapid prototyping machine made in the lab we produced for them with our colleagues in Shenzhen. These are kits of all the electronics facilities. These are remote interfaces to the larger machines we couldn't send home, to this idea of bringing the labs to the students. And most recently, what we've been doing to support that is in the lab, you can make a machine, but you can't make the things that go into the machine. This is a super fab lab. This is the first one we did analogous to the lab I run at MIT. This is in Kerala in the south of India. The next one we're doing is in Bhutan. These are $1 million super labs. Each of the machines in the lab cost about $100,000, as much as a regular lab. But these are the more advanced manufacturing tools that let you make the parts that go into the machine. And so to widely deploy $10,000 and $100,000 and $1,000 labs to reduce the cost down, you need to invest up in the capacity to do it. So starting to create this global network of these super labs. So then let's keep scaling. So that's rapid prototyping of rapid prototyping machines. On Earth, there's billions of people. In the computing era, we got to billions of computers when they became truly personal. So now PCs and then smartphones. And here there's a problem. This thing you can't read up top on my screen is the inventory in one of these labs. They can make everything I'm describing, but there's still a global supply chain for the parts. And down below is just part of the electronics inventory to make the circuits. And so I buy parts from a vendor, DigiKey. DigiKey sells hundreds of thousands of types of resistors or capacitors or inductors or connectors. But conceptually, those are made out of just a few material properties. One is conductivity, one is insulators, one is resistivity. And so in theory, you could make all of these out of just a few parts, an inventory of a few parts, making the full range of electronics. And so that's not a new idea. That's actually 4 billion years old. The life is based, of course, on 20 amino acids. And what's interesting about the amino acids is they're not interesting. They're just typical. They're hydrophobic, hydrophilic, basic, acidic, but you can compose those properties to make muscle motors, olfactory receptors, synapses by composing those typical properties. And so that's inspired us to look at, can we do the same thing for engineered systems? And so this is an assembler we built that's like a 3D printer, but instead of printing, it places. And what it's doing is it's placing micro building blocks. And then the micro building blocks it's placing are to make micromechanical systems. And so a rigid part is rigid, a flexural part bends, 2 of them does parallel transport, 4 is a 4-bar linkage. A 1-bit actuator moves, 2 of them does cyclical motion. And when you add all of that up, then this is a motor, but it's a motor made out of a discrete assembler that builds motors, not out of a big supply chain, but just having, in that case, 4 or 5 building block part types. And so that's led to a lot of commercial activity. The work to make the building blocks has led to a company we're spinning off. This is my student, Prashant. Jeff was the former number 2 at Amazon, to do direct write fabrication of these sort of micro electromechanical structures. And then this idea of not printing or cutting, but assembling and disassembling on bigger scales led to this collaboration with NASA to make large scale aerostructures by linking together simple cells of building blocks. There's a longstanding goal to make aircraft that instead of control surfaces can change their shape, but the mechanisms were expensive and complex. Here, what we did is by just taking rigid and flexural building blocks, we showed you can assemble volumes that have the world's highest modulus for an ultralight material, but you can design in deformations for how they shape to be able to discretely assemble aerostructures. This is the size of NASA Langley's biggest wind tunnel. And then to build them, it leads to a really interesting kind of new robotics. So this is work by my student, Ben Jeanette. This is a robot that locomotes on the structure it's building. It navigates relative to the structure. It detects and corrects errors in its placement, and then it can place these structural building blocks. And so that a small relative robot can build a structure much larger than itself. And then you can coordinate the behavior of swarms of these robots. And so you can think about this as a relative robot. It's a robot, it's a material robot system. It's a robot that you can't decompose from the material designed to build with the materials. And Ben is right now commercializing that in a new company, Discrete Lattice Industries, aimed at on-site tooling-free performance of large, high-scale, high-performance architected structures. So that's at the million stage. And then ultimately what happens at the stage after that. So there's on the order of 1 trillion things on Earth. And by that, what I mean is 1,000 is a typical number for the number of things around a person. And this is the scale of the Internet of Things era. And so here's a smart thermostat, and there's trillions of these coming. And these smart devices, if you look at the Nest thermostat, matches the performance of the PDP. So the $100,000 2-ton computer that filled a room and was used to start the internet, essentially the same performance now goes into this thermostat. And so it's not an analogy, it's not a metaphor. The scaling of 1, 1,000, 1 million, 1 billion, 1 trillion is what happened to computing. And so now if we look at that stage in digital fabrication, there's in turn another scaling issue. So we're living through what appears to be an AI revolution. But if you look at the numbers, a supercomputer today can do 10 to the 17 ops per second. And the brain today can do the brain can do on the order of 10 to the 17 ops per second. And so the real revolution that happened in the last few years is the performance of high performance computers roughly match the operational capacity of our brains as measured by the number of synapses and the firing rate. In turn, to make a supercomputer with the complexity of a brain, you need exaflops and petabytes. Those are on the order of 10 to the 16 transistors. The fab making them, if you look at the resolvable elements and the rate they're being produced, is generating about 10 to the 10 parts per second. As you've been listening to me, you've been placing on the order of 10 to the 18 parts per second. So 10 to the 8 difference, a factor of 10 to the 8 in your performance versus a state-of-the-art chip fab. And this at heart is because of, again, a 4 billion-year-old idea, ribosomes. So the reason you can be a factor of 10 to the 8 more performant than a chip fab is ribosomes make ribosomes. So the ribosome is the molecular assembler that builds. It is digital. It's digital, not meaning ones and zeros, but digital doesn't mean ones and zeros. The heart of digital is something Claude Shannon showed a number of years ago, which is I could send you my picture and voice as an analog wave and it would degrade with distance. I could send it, as I'm doing now, by coding it in symbols. If I code it in a symbol, if the noise is above a threshold, you'll make a mistake. But if the noise is below a threshold and you decode the symbol, for a linear increase in the physical resources representing the symbol, there's an exponential reduction in the error that you'll make. And that exponential reduction is what gives the fidelity that lets us create the internet and lets me talk to you. In the same way, the ribosome elongating a protein makes an error about 10 to the 4. DNA replication is more sensitive. It adds an extra error correction step and makes an error on the order of 10 to the 8. That coding construction is what makes the exponential complexity of biology possible. And right at the heart of it is a recursion. Ribosomes are slow. They elongate at about an amino acid per second. You can make an elephant 1 molecule per second because ribosomes make ribosomes, since you can have trillions of them in a cell. So you can work with that system. This is work we did with NIST and JCVI on a minimal synthetic genome. More recently, we've shown how to edit that to control cell size, discovering interesting functions that weren't appreciated in these minimal genome cells with only a few hundred cells. This is another project where we used electrospinning to make nanostructured environments for cell growth. All of this is manipulating biology to code what it does. But you're, of course, limited by the materials of biology in doing that. And so I've been very interested in an analogy, which is biology starts with a linear coding sequence in an mRNA that turns into secondary structure of alpha helices, beta sheets. These become a tertiary structure, things like electron donors and acceptors. Then they become quaternary structures, things like olfactory receptors or muscle proteins. And there's no reason we need to be restricted to doing that with amino acids. And so my lab has been studying, can we take a very small set of building blocks, compose them into functions, compose those into modules, and make those into systems to build up that same sort of hierarchical complexity, not out of an inventory of hundreds of thousands of parts, but out of a very small set of building blocks. So before I showed you making micro robots, these are now micro mechanical robots designed to make micro mechanical robots to be able to do that essential recursion of the exponential growth. And this leads to a few profound places. This is a fun program that's bonus material for the movie The Martian. Historically, what's called ISRU, in situ resource utilization, looked at how you go to the moon or Mars and you create a civilization. And it assumed you essentially need the Industrial Revolution. You need the ability to produce the inventories of hundreds of thousands of parts. And what's behind me, you should now recognize from what I've been talking about, what we're coming to appreciate is that's not right. Instead, you essentially want to create life in non-living materials. You want to create about 20 material properties again, like conducting, insulating, resistive, that aren't extreme or just typical, create them in building blocks that with these digital materials, these digitized materials. And by digital materials, what I mean is materials with coded construction that let the local geometry determine the global structure, that let you detect and correct errors, that let you join dissimilar materials, that let you unbuild. All properties familiar to a child with Lego, properties familiar to a molecular biologist, but not historically part of advanced manufacturing. And we're discovering you can really do that for all of modern technology. And so where that leaves is the founders of the modern digital revolution include Alan Turing and John von Neumann. But it was kind of an accident. Turing studied theoretically the Turing machine, which wasn't really physical. The head and the tape were distinct, even though in physics those are coupled. Von Neumann created the von Neumann architecture. He never really wrote about it. He wrote beautifully on other things. You just wrote this memo on programming an early computer. So they're credited with creating the modern structure of computing, but those were not core contributions. They weren't architectural. Both of them at the ends of their lives studied how computation relates to fabrication. So von Neumann studied self-reproducing automata, how a computation can communicate its own construction, interested in understanding the heart of how life works. Turing studied morphogenesis, how genes give rise to form. So your body doesn't store anywhere the fact that you have 5 fingers. It stores a developmental program that gives rise to 5 fingers. And it does that for a reason very closely coupled to how AI works. Most changes to the genome would be fatal or inconsequential, but not interesting. The heart of AI is not better ways to search, it's where to search, in the same sense that search over the part of the genome that gives rise to these developmental programs is what lets evolution discover the diversity of life. And so both of these at the time were theoretical, and we can now really do them physically. We can really blur this boundary between animate on automata, creating lifelike properties in inorganic systems to breach the boundary, to break down this boundary between digital and physical worlds. And so in the scaling of 1,000 million, billion, trillion, I literally mean a trillion fab labs, just like a trillion smart thermostats or like PDPs. What you should take from this picture, though, is this ranges from today to ultimately decades in the future to finish this research roadmap. But you can see them all here today. All of these exist in the lab. They're all happening in parallel, but the impact coming out into society ranges from immediate to decades in the future. I described that story in this book, and there's a number of translations, including a Chinese one. I wrote it with my younger brother, Alan, who ran at the time the biggest video game studio, Activision, and my older brother, Joel, who ran the National Labor Relations Organization. And the reason we wrote it is when I would talk about this research roadmap, I would get up to where I just finished and stop and people would clap. And Joel and Alan would be concerned that I was being naive, not about the technology, but about society. So remember, Gordon Moore forecast what became Moore's Law, but he didn't anticipate spam and fake news and income inequality and all those issues we've been dealing with. In the same way, Joel and Alan's concern was we could do 50 years of digital fabrication scaling, but how do you ensure access across society? How do we handle diversity and inclusion? How do you anticipate all those challenges we've faced in the other digital revolutions? And their key point is rather than waiting for them to happen, right now is when you can shape how the technology impacts society. And so these really profound questions about if anybody can make anything anywhere, how do you live, learn, work, and play, are really being shaped now. And so the technical project is the science and technology of digital fabrication, but the kind of meta project is what does that mean for society, for some of the most profound challenges and opportunities, ultimately getting at, I'd say, my favorite question, which is how can we take better use of the brain power of the planet? And so with that, I'll stop and be happy to take questions.
Thank you so much, Professor Gershenfeld. This is wonderful. I would like to follow up with a few questions from the audiences and myself. The first question actually came from myself. I know that during COVID, you and your team and Fab Lab in general had done a lot to combat the COVID, specifically, for example, like the PPE manufacturing. I wonder what is the most practical question you have confronted in this process, and what had inspired you the most?
Yeah, so I'd say the biggest there were three surprises maybe in the PPE. It's again, let's see, PPE is where we started, and then there was a whole life cycle from PPE to respiratory assistance to help with recovery and testing. One of the surprises was each of those things raises fairly substantial research questions, and so in a Fab Lab you could produce a nasal swab or a shield, but you need to do things like computational fluid dynamics to study virus propagation that's way beyond the skills in a lab. So one observation was the need to couple fairly basic research questions with these urgent responses. In turn, what that led to was collaborations of people who had just never worked together. So we had scientists in the lab with community activists, with government regulators, with manufacturing experts, with local activists, all discovering they really needed to work together. They considered all those other people sort of alien to them. And so discovering the need for these very different groups to work together was the second surprise. And then the third was this missing middle between do-it-yourself and mass manufacturing, and the urgency of scaling up these distributed responses. Eventually, from the distributed response, it can migrate into mass manufacturing. But what's coming out of that is there's computing perhaps on your wrist, there's computing in your pocket, computing on your desk, computing in your house, computing in if you're in a university, computing in a cloud. We have all those scales of computing, and we don't pick which is best. We need all of them. And so in the same sense, in between traditional mass manufacturing over here and traditional do-it-yourself over here, this helped fill in all of these intermediate stages that each are useful and was something coming in the future, but was accelerated by the pandemic.
Thank you so much. I have a few questions from the audiences as well. The first question is regarding to if there's anything in human beings that cannot be replaced by machines.
So what's important, let's see, I believe in history. And so in thinking about machines versus people, I think there's two common mistakes in how that's discussed. So one of them is fear of the rise of the machines assumes automation and machines are sort of done to people and harm people and it is in competition with people. And what that misses is the possibility of the machines being created by people. And so you can think about what I've been describing, not just as digital fabrication, but kind of personalizing automation. So if you're running a small local business where traditionally you didn't have access to automation, you can be empowered by creating, in a bakery, tools that help the operation of the bakery. We see emerging a kind of empowering of individuals by providing expanded access to automation. So one of the distinctions is the point that it's not just faceless industry displacing people, it can empower people. But the second also is to be aware of these battles tend to get settled by irrelevance. And by that, what I mean is there was a time where it was interesting to race horses and trains. Then eventually the trains started beating the horses, and we now have trains, but it doesn't mean we've gotten rid of horses. Horses still do a useful function. There's a time where the most interesting question in all of computing was computers and humans playing chess. And it was seen as epical. Initially, it was seen as hopeless for computers to win at chess. Then epical, this life-changing moment when computers could beat people at chess. Now, computers easily beat people at chess. That's no longer interesting, but people still play chess. And so it's important to have a sense of sort of historical humility that each time each of those transitions come, they tend not to trivially obsolete. We win those battles by irrelevance. So there are a number of things to worry about. That for me is not one of them.
Thank you. Then the following question is regarding to how 3D printing might help the drug discovery and manufacturing of drugs. So the question is, can 3D printer print small molecule drugs or large molecule drugs with known structures?
So there's a really interesting recursion, which is, I mentioned a bioacademy. And where that started from is I teach my class at MIT to the MIT students, but with the Fab Academy, I'm now teaching networks all around the world. And so my colleague George Church at Harvard was struck by the same thing, that he can teach a room full of students at Harvard. He can have an online class, but you can't learn biology online. So this idea of the bioacademy. And what that's based on is another kind of recursion, which is a fab. So many of the tools in a biology lab, as viewed from a non-biological engineer, are expensive and don't work well. Just sort of the market that sells to biologists. And so there's this interesting recursion that the tools in a fab lab can make a bio lab, and then with the bio lab, you can make materials for the fab lab. And so a 3D printer today can't place molecules, but the immediate answer is with the 3D printer today and other tools in the lab, you can make the machinery to make a biolab to then do biotechnology to place molecules. And so that's the direct answer, expanding access to biotechnology. In turn, there's a number of interesting projects around that. We're working with the National Institute of Standards in the US to develop machines for material science that let you do rapid prototyping of materials development and develop models of the materials. And so the machine building is leading to interesting work on materials. And in turn, that collaboration includes a platform called Materiome, which is looking at open designs for sustainably sourced biomaterials. So rather than things like petrochemical supply chains, how you can use this instrumentation to design sustainable biomaterials is a very active research area. So the machine in the lab doesn't place the molecule, but it makes the machine that can then do the biotechnology for the growth. And I should note, that is one of the things that does scare me. You can do very scary things once you have access to those tools. And so an important part of that is we found that you can't regulate this in the way you traditionally regulate safety, because there's no central points of control in access to the machines. What you can do is you can provide access for transparency. You can provide incentives for people to do this in a transparent, shared way rather than in private, which is a large discussion about the biosafety.
Thank you so much. The next question is from Xinjie. Thank you so much, Professor Gershenfeld. Very inspiring talk. Can we propose some new versions of Moore's law extending to the development of other fields? For example, how do you see the evolution of biotech charged by digitalization or automation?
So, yeah, to explain what I call Lass's law, Sherry Lassiter runs the Fab Lab program for me at MIT, and she leads what's now the Fab Foundation we spun off. She has many skills, but she's sort of messy in her office. And she had a pile of papers of people saying, I want to join the Fab Lab network. And that pile kept doubling in size. And so as a joke, she started talking about it's like Moore's law. And then when I went back and did the data on the rate of growth, I saw it really was exponential. And so that's why it's come to be called Lass's law. And now Moore's law, he was initially counting transistors, but it also shows up in the number of chips and the number of IP addresses, in the clock speed, in the power, in all of those attributes. So in the same way, number of fab labs is one crude statistic, but there's similar statistics in the number of parts made, in the resolution of parts, all of those things. So, but it's important to be clear that what made Moore's law possible was digital. So these core profound digital properties, which aren't ones and zeros, it's this property of exponential reduction in error, restoration of state, hierarchical complexity. That's what makes Moore's law a property. At heart, it's a digital scaling property. And so when I say digital fabrication, there's a 1952 meaning of a computer controlling a machine. There's, say, a year 2000 meaning of not additive versus subtractive, but assembly versus disassembly, digitizing the materials. And the really profound meaning is the 4 billion-year-old meaning of the age of the ribosome, but now that we're doing today in the assembling assemblers, in this merging of computation and fabrication. And those are what are putting fabrication on a Moore's law type scaling, this digitization of fabrication. And so other things to have that scaling need to be digital. And a really great example is my older brother, Joel, who's an expert in organizations, describes it as if machines that make machines, you need organizations that make organizations. You can't build, so we've had a lot of trouble with traditional business school expertise and the Fab Lab network, because if you take one of these grassroots inventors and a traditional entrepreneur, they get mad at each other because they feel like they're not helping each other. And what's going on is the traditional script of how you run up a startup and go to market doesn't really apply to this much more distributed model. And in fact, many of the motivations for doing this aren't simply money, but like what we're doing in Bhutan of sort of looking beyond just economic output to well-being as the output from it. And so there's a real need for organizational innovation to keep up with it. And coming back to the question, there's a need for scalable organizational innovation that can follow the scaling of the technology.
Thank you, Professor. So we're running out of time here. So I'm going to be ask the last question on behalf of the audience. This question is from Mark. Professor Gershenfeld, along with the passing of the Strategic Competition Act of USA, how do you think of your fab cooperation network with Shenzhen? Any forecast to China's AI development? Thank you.
Yeah, so this is a really interesting topic. If you look at where the press covers, there's lots of battles today. But if you look around it, there's a much more hopeful and interesting future. So there's a lot of coverage in Spain of Catalan separatism, but that doesn't have much to do with the urgent needs of the economy. If you look in Barcelona, where the press isn't covering, is this amazing project on Fab Cities. In the same sense, there's a lot of history and a lot of concerns in the relationship between China and US officially. But there's this deep connection with the Shenzhen ecosystem in the technology that powers what I'm describing. We're big fans of it. There's lots of traffic back and forth. And around that is a really interesting transition. In a world where Barcelona makes what it consumes, you don't need the Chinese manufacturing ecosystem to mass produce the products. What you do need, though, is the enabling technology for it, the things that let Barcelona produce. And so there's a great collaboration with the Shenzhen manufacturing ecosystem, not on the finished products, but with colleagues like at Seed and a number of others on the things that empower people to make locally. And it's crucial to the success of this initiative. And then in turn, in China, in India, where a lot has been focused on external production, this in turn helps redirect it also internally to empower internally, not just export. And so there's a really rich collaboration at the frontiers of this digital fabrication revolution in all of the countries that officially seem to have tension, but there's this sort of really pleasurable, really deep collaboration in the enabling technology for it that's kind of away from where all the attention is today.
Wonderful. Thank you so much, Professor Gershenfeld. Thank you so much for attending our conference, and it's really nice to meet you today. And I will also like to thank all our audiences for attending our conferences from all around the world. Please stay tuned for our next session and hope to see you soon again in the future. Thank you.
My pleasure. Thank you. Bye-bye.